We're going to continue our investigation of subspaces with a couple of technical lemmas which say that if you take a sum, as we're going to define, or an intersection of two subspaces, then the result is again a subspace. So here's the first one. I'm going to make a definition of the sum of two subspaces. If you have two subspaces x and y of a vector space V, then we define the sum x plus y to be all the things you can get by adding an element of x to an element of y. So the set of all x plus y, where x comes from x and y comes from y. Then what the lemma claims is that that is a subspace of V. So let's do the proof. You will remember that the definition of subspace comes in three parts. You've got to contain the zero vector, be closed under addition, and closed under scalar multiplication. So let's do the first one, the first one which is containing the zero vector. So x is a subspace of V, so the zero vector, 0 subscript to V, is in X. And Y is a subspace of V, so for the same reason, the zero vector belongs to Y. So that means the sum of the zero vector and the zero vector is in X plus Y. And of course the zero vector plus the zero vector is the zero vector. We check part 1 of the definition of being a subspace. Part 2 is closure under addition. I have to take two things in x plus y and prove that their sum is in x plus y. So a typical element of x plus y looks like an element of x plus an element of y. So here we've got two such typical elements, x plus y and x prime plus y prime. So there's no intended relation between x prime and x, they're just two random elements of x, and y prime are just two random elements of y. And as usual, we'll keep this convention of underlining things to remind us that these are elements of vector spaces and not necessarily numbers. So we're to prove x plus y is closed under addition. I have to show that x plus y plus x prime plus y prime is again in capital X plus capital Y. Well, vector addition is always associative, and associativity tells you that you can re-bracket sums any way you like. We also have commutativity of vector addition, which means I can move vectors around within a sum without changing its value. So doing those things, I can rearrange this just to be x plus x prime plus y prime. Now, x plus x prime is in X because X is a subspace, so it is itself closed under addition. So similarly, y plus y prime, it's in Y because Y is closed under addition. So this thing is an element of x plus y. We've just seen that this thing is an x and this thing is an y, so that thing really is an element of capital X plus capital Y. So we've just shown that capital X plus capital Y is closed under addition. The final property is scalar multiplication. We have to show that x plus y is closed under scalar multiplication. So we let this be an element of our sum. And we let A be a scalar. So what that means is if V was a real vector space, then A is some real number. And if V was a complex vector space, then A is some complex number. So now I'm to check that A times x plus y is an element of capital X plus capital Y. But we can use the vector space axioms. So one of the vector space axioms tells me that that is AX plus AY. Now the first thing, this is an element of X because X is a subspace and so closed under scalar multiplication. And the second thing here is an element of Y because Y is a subspace, so it's closed under scalar multiplication. So this is in X plus Y as AX is in X and AY is in Y, because X and Y are themselves subspaces. Okay, we checked all three conditions, and so this thing X plus Y really is a subspace of V. We're now going to do the same thing for intersections. So here we take two subspaces, capital X and capital Y, of a vector space V, and the claim is that the intersection of X and Y, and that has its ordinary set theoretical meaning, X intersect Y being the set of all things which are both in X and in Y, that thing is a subspace of V. Let's do the proof. As usual, this is a claim that something is a subspace, so we do it just by checking the axioms. Well, the 0 vector is in X because X is a subspace. The 0 vector is in Y because Y is a subspace. So the 0 vector belongs to both X and Y. We've proved that the intersection passes the first part of the subspace test because it's got the 0 vector. So now let's show that the intersection is closed under addition. So let's say Z and W are elements of X intersect Y. I have to prove that Z plus W is an element of X intersect Y. So first of all, Z and W are in X, which is a subspace of V, so which is closed under addition. So Z plus W is again in X. X is a subspace, so it's closed under addition. But of course the same thing holds for Y. Z and W are in Y. Y is a subspace of V, so Z plus W is in Y. Putting those two things together, we get that Z plus W is an element of X intersect Y. And we've shown that X intersect Y is closed under addition. And the last one is scalar multiplication. So we'll let Z be an element of X intersect Y, and we'll let A be a scalar. And again, what that means is if V is a real vector space, we're letting A be some real number. And if V is a complex vector space, we're letting A be some complex number. So AZ is a scalar multiple of Z. Z is an element of X. So AZ is in X because X, being a subspace, is closed under scalar multiplication. For exactly the same reason, Z is in Y. Y is a subspace. Subspaces are closed under scalar multiplication. So A times Z is in Y. So we've established A times Z is in both X and Y. That means it's in their intersection. We've proved that this intersection is closed under scalar multiplication, so we're done. We've checked that X intersect Y is a subspace.